the characteristics of the cubic function. Okay, so make sure that you've studied all of that, because without it, you're not going anywhere. So the rules for sketching the graph of cubic functions really are as follows. Generally speaking, you would only calculate the point of inflection if they asked you to. It's not typically something that you would show on a sketch, but it is a question that often gets asked. Okay, so what do we need to show? All right, well, we've got to show the y-intercept, we've got to show the x-intercepts, and we've got to show the coordinates at the turning points, okay, when we sketch a cubic function. Irrespective of whether they get you to sketch the function or not, they will expect you to be able to work out the x coordinates, they will expect you to work out the coordinates at the turning point, and they will expect you to be able to calculate the, at the very least, the x coordinate at the point of inflection. Okay, so whether we're asked to sketch or not, these are things that are definitely going to be examined. So they're very important, and that's why I wanted to spend at least today's lesson on talking about them. All right, so what I want to do is dive right in, and I'm hoping that as we go through this, what we spoke about in our last lesson, you will connect the two together, and I'm obviously going to try and help you to be able to do that. All right, so if they say to us, sketch the graph of the function, they want us to show the y-intercept, the x-intercepts, the coordinates of the stationary points. Okay, that's the minimum that we need to show. All right, if they give us the graph of f of x equals x cubed minus 6x squared plus 9x, they're actually being quite nice to us, because we don't have to use factor theorem to determine one of the factors of this cubic are, because we can factorize out x as our highest common factor. All right, so let's do the x-intercepts first. Okay, this is something that we actually know how to do. We make y equal to 0. And now we factorize. Okay, so we're going to take out x. This leaves us with x squared minus 6x plus 9. And then we factorize our trinomial, and we're going to end up with x minus 3 times x minus 3. So how many x-intercepts are there in this function? Remember, there can be 1. There has to be at least 1. There can be 2. Or there can be 3 x-intercepts. How many are there in this particular function? Exactly, there are 2. Excellent, lovely. So we have 1 where x is equal to 0, and we have another one where x is equal to 3. Lovely, guys. Perfect, perfect. Now, what can you tell me about the x-intercept where x is equal to 3? There's something special about that point. Aha, Boutle nailed it. Okay, so it is also a turning point. How do you know, Michelle, how do you know, Belinda, that it's also a turning point? What's the clues that give this away? Exactly. Exactly. The repeated bracket. Beautiful, Hope. I couldn't. Yes, Mohammed. The same bracket twice is the dead giveaway. Okay. So that means that our x-intercept is also a turning point. All right. So now we know for this particular function, we've got our x-intercepts and at least one turning point. What is our y-intercept? I'll go back up again. What's the y-intercept? What's the value or the coordinates of the y-intercept? Exactly. All right. So quite right. This particular graph goes through the origin. All right. So now we've done our x and y intercepts. Easy. Same thing that we've always done all along with functions. For x-intercept, let y be 0. For y-intercept, let x be 0. Now we're going to work out the coordinates at the turning point. Okay, so we want to work out the coordinates at the turning points next. All right. What is the deal with the turning point? What specific thing do we know about the turning point? Exactly. The first derivative is 0. The gradient is 0. Okay, very, very good, Kanisile. Lovely. Okay, the gradient is 0. The first derivative is 0. So I want you guys to take the first derivative. We're going to make it equal to 0, and then we're going to solve the x coordinates at the turning points. Okay, so I'm going to let you guys do that. And then we'll check and we'll move on. Just put that down there as well. Exactly, Hope. Lovely. All right, I quite agree. Okay, so Hope, you've written f prime x equals 3x squared minus 12x plus 9. Fantastic. Yes, Tsepiso, lovely, 100%. And what do we have to do with f prime x now? We have to make it equal to 0. Okay, because the gradient at the turning point is 0. The gradient at the turning point is 0. Lovely. Now, matrix, you get a mark for writing down the first derivative. You get a mark for saying that the derivative is 0 at the turning point. Okay, so those are two very important lines that you must show. What are we going to do next? Absolutely, Buhle. Okay, so now we need to solve for x. Exactly. All right. So what I would do here, Kolofelo, is I can see I've got a 3 and a 12 and a 9. I would divide through by 3. And now we're going to factorize. Yes, Kolofelo, I get the same answer. Good job. Very nice. And I'm so glad you didn't leave off the equals 0. Okay. Lovely, Kolofelo. I'm so glad you put that out there. So important. So many matrics do that. And often on this line, and not just in this section, but in lots of sections, this line here, when you factorize a trinomial with the view of solving the equation, if you leave off the equals 0 and there's an accuracy on that line, the mark's gone. Okay, what a pity that is, especially if you know how to factorize. Okay, so don't leave off the equal 0 when it's meant to be there. All right, and now we're getting an answer we expected. Remember, we said we knew that x was going to be equal to 3. Or our other turning point is where x is equal to 1. All right, we know that 3 is a turning point and an x-intercept, so there's no point in us working out what f of 3 is, because we know that f of 3 is 0. Right, but we do need to work out what f of 1 is. Okay, so f of 1, show the step 2 matrix, and then just use the calculator to work out the answer. I agree, Belinda. Sure, you guys are on fire tonight, hey? Wow, wow, wow. Nice. Good job. Good job, guys. Okay. So there we go. We've got the coordinates of our turning points. We've got our y-intercept, our x-intercepts. We've got the coordinates of our turning points. Now, let's not worry about the point of inflection just yet. Let's go and sketch this graph, and then we can talk about the point of inflection. Okay, so it's got a y, so we know it goes through the origin. We know it's got an x-intercept at the origin. We know that it's got an x-intercept at 3. We know that it's got a turning point at 3 and 0, and we know that it's got a turning point at 1 and 4. All right. I want to ask you guys, if you have to describe the shape of this function using the words concave up and concave down, just hang on a second. I'm going to write a reply to somebody, but just think about it. How would you describe this graph? Is it first concave up and then concave down? Or is it first concave down and then concave up? Yes, Michelle. Okay, you've got it. All right, perfect. How did you know that, Michelle? A is positive, quite right. Okay, so Belinda, it's going to be concave down first, okay, and then concave up. Because, just like Michelle was saying, the number in front of the x cubed is a positive 1. So that means that A is positive. So when A is positive, that means that the graph is shaped like that. Concave down, and then concave up. All right. If A is negative, then the graph is concave up and then concave down. Okay, so make sure that it's all right, Belinda. You know how many mistakes I make in a day. That's nothing. Okay, mistakes are how we learn. It's no problem at all. All right, so concave up and then concave down if A is negative. All right. We do, Neliswa. And this is important because we also need to know which one of our turning points is going to be our maximum and which one is going to be our minimum. Okay, so we know that this particular graph is going to be the blue one. All right, so this blue guy over here that I'm busy putting green arrows on the end. All right, how do I know what are the coordinates at the local maximum and what are the coordinates at the local minimum? What am I looking for specifically here? Can anybody tell me? Not the second derivative, Aisha. I'm sorry, the second derivative is about concavity. Okay, the second derivative is all about concavity. We're talking about how, not necessarily, Tsepiso, not necessarily. Okay, so hang on a second, guys. Let's just go over here. All right. If my graph is shaped like this, okay, and my x-axis is here, okay, numbers get bigger going in this direction to the right, don't they? And they get smaller going in this direction to the left. So the x coordinate at this point over here is bigger or smaller than the x coordinate over there. Is this number the smaller one or the bigger one? It's a smaller one, absolutely. So any value that lies to the left of another one on a number line is going to be smaller. This one is going to be bigger. So this is the smaller x, this is the bigger x. So if we take what we've got here, remember our coordinates at our turning points. Okay, it's not that my x-axis is in the right place, it isn't, but anyway, let's just get rid of the x-axis. They're not in the right place in any case, right? But this one over here Oh, freak. Hang on a second. Ha ha. That's the best part about this. You can just go undo when you make mistakes. But it was so easy to do that in maths. Hey, just click on undo. Okay, so we've got the number 1 and we've got the number 3. Which one's the smaller number? The 1, hey, all right. So that means that 1 and 4 has to come first. Oh. Okay, 1 and 4. Why are you not going on my pen? Okay, 1 and 4 has to come first. And 3 and 0 has to come second. Does that make sense, guys? So my local maximum is going to be my smaller value of x when the graph is concave down and then concave up. So in other words, when a is positive. Okay, and my minimum is going to be here at my bigger x. Does that make sense, everyone? Okay, if my graph was first concave up and then concave down, my minimum comes first and my maximum comes second. So my minimum is going to be where the smaller x is, and my maximum is going to be where my bigger x is. Okay, so let's say that we had a maximum. Let's say here the x coordinates at the turning point. One was x equals -1, and the other one was where x is equal to 3. -1 is smaller than 3. So that's why the -1 has to be here, and the 3 has to be there. Does that make sense? So you see how important the shape is, okay, in working out which x value or which pair of coordinates go at the maximum and which pair of coordinates go at the minimum. You have to look at those two things together. How are we feeling? Thumbs up, thumbs down. Thank you, Neliswa. Cool, everybody. So this actually is where my x-axis is going to be, isn't it? This orange line that I've drawn here. Maybe we can make our x-axis a different color. Make it blue. Okay, so we've got a blue x-axis now, guys. All right, so there is our x-axis. Because remember, 3 and 0 was also our x-intercept and our turning point. Now, our y-axis. All right, where did the graph cut the y-axis? Remember, it was here at 0 and 0. Okay, at 0 and 0. So where is 0 going to be? Where is the y-axis? Sorry, where's the y-axis going to be in this case? Remember, this x-intercept over here, let's just fill that in because that also gives us information. Then we can put our y-axis in. Actually, let's do that first. Okay, so our x-intercept was at 0. So what can we say here conclusively? Our x-intercept and our y-intercept in this case is the same point. Okay, it's the same point, which means that our y-axis matrix has also got to go through, not that one, sorry, this one, that color. It's got to go. Oh, I'm just going to move it a little bit. There we go. It's got to go through there. Okay, does that make sense to everybody? Yes, Belinda, the point 0 and 0, quite right. Okay, so 0 and 0 is our one x-intercept, and it is also our y-intercept in this case. All right, and again, 1 and 4 is a point in the first quadrant. Okay, so, you know, where the point is, you have to be able to plot it correctly for that particular quadrant. Okay, does that make everybody, is everybody happy? Right. Let's talk about the point of inflection now. Yes, okay, cool. All right, if you're not, please do say so. I've got no problem going back and explaining what I was talking about. Okay, so the point of inflection. Okay, so the point of inflection is a point on the graph where the concavity changes. Okay, so the concavity changes from being concave down to concave up. Absolutely, Neliswa. Thank you so much for that. It changes from being concave down to being concave up. All right, so this particular graph, remember, is first concave down up to that light green dot. And after the light green dot, it is now concave up. Okay, so here where I'm putting the pink highlighter, it is now concave up. Okay, and just like y can be positive or negative or 0, gradient can be positive or negative or 0, concavity can be positive or negative or 0. Okay, so concavity is going to be, let's just clear a little bit of space here, right? So when the graph is concave down, concavity that means concavity is positive. Sorry, concavity is negative. Concavity is negative if it's concave down. Over here, where it's concave up, then the value of the concavity is going to be positive. All right, and directly here in the middle, in between these two, okay, over there, that is where the concavity is 0. Okay, and that point there is called the point of inflection. So at the point of inflection, the concavity is 0. Okay. We use the first derivative to describe gradient. We use the second derivative to describe concavity. Okay, so just like I will say the gradient is 0 at the turning point, I can say the concavity is 0 at the point of inflection. Okay, does that make sense to everybody? Okay, so gradient can increase and decrease. So concavity can also be positive or negative. When it's concave down, it's negative. When it's concave up, the measure of concavity is positive. Okay. How we feel? Yeah, lovely, Neliswa. How are we feeling so far? Okay, cool, guys. Thank you so much for all that feedback. Let's just finish this off. Okay, so we can work out the x-coordinate at the point of inflection. Okay, and it is in fact something that they do ask us to do, because they often one of the questions that gets asked is, for which values of x is the graph concave down, or for which values of x is the graph concave up? Okay, they love to ask questions like that. So often out of 2 marks, and it's actually not a particularly difficult question to answer. If you, yes, Cassandra, with pleasure. Okay, so Cassandra's just asked me to explain the concavity part again. All right, so what I'm trying to get you to understand, Cassandra, let me just move over and draw over here, is that we can look, or we do look at 3 things when we're talking about the cubic function, okay? We look at y, which is f of x. We look at gradient, which is f prime x. And we look at concavity, which is f prime prime x. So this is output, or y. This is gradient. And this is concavity. Okay, so concavity works like this. Anything that is that shape, that is called concave up. Anything that's this shape is called concave down. Okay, so if we go and we have a look at our pink graph over here, can you see, Cassandra, over here to there, it's concave up. Okay, then the place at which it stops being concave up and starts being concave down is the point of inflection. Now the graph is concave down. Yes, Tisha, that's exactly right. Okay, Cassandra, does that make a little bit more sense now? No problem. All right, Tisha, as you said, all right, when we want to work out the coordinates, where were we? When we want to work out the coordinates at the point of inflection, we're going to let the second derivative be equal to 0, okay, because the measure of concavity at the point of inflection is 0. So to get our second derivative, what do we do to the first derivative? We have to get our second derivative from the first derivative. What do we do to our first derivative?
The power rule.
Exactly. We're going to apply it. We're going to differentiate again. Quite right, guys. We are. I just want to clarify something. Hope. Yes. Yes. That's exactly what I'm saying. Okay, quite right. Now, Hope said this, and I think this is a really important thing to point out to you. All right, Hope, where the dark green is and it's concave up, you're quite right. F prime prime x is greater than 0. Here, where it's blue and it's concave down, f prime prime x is smaller than 0. Exactly. Okay, here at the point of inflection, there, stupid pen, f prime prime x is 0. I just want to reply to a question, and then we're going to talk about the coordinates at the point of inflection. I'll call a fellow, that's lovely. All right, sorry, I just had to answer a question in the chat. Let's go back. All right, so Colofello's already done it. All right. What Colofello, or tell you what, Colofello, are you happy to share what you did with us? Are you happy to share your method?
Yes, ma'am.
Go for it. Tell us what you did.
So, ma'am, I differentiated the equation that we first differentiated earlier.
Okay, lovely. So that was this one over here, the 3x squared minus 12x plus 9.
Yes, ma'am.
Okay, so you wrote f prime prime x equals
6x is equal 6x minus 12.
lovely, lovely, lovely. Keep going. I love it.
And then I took the 12 to the right and then divided the 6 with the 12, and then I got the x value 2.
Beautiful.
Yeah,
Don't forget about making it equal to 0, okay, Colofello? Don't want you to
yes,
lose
ma'am.
any marks. Okay, but
Yes,
you're quite right. If you take
and
that
then,
over to the other side, x would be equal to 2. And then what did you do?
and then I substituted the 2 from the first equation.
Okay, so you took the 2 and you subbed back into the original equation. Okay, so x cubed minus 6x squared plus 9.
Yes.
X cubed minus 6x squared plus 9x, and then you ended up with an answer of
2.
2 as well. Absolutely, you would in this case. All right, so you worked out the y coordinate at the point of inflection, which there's nothing wrong with that for the coordinates at the point of inflection. So now let's go up. Typically, it would just be the x coordinate that we would need, but nothing wrong with working out the y as well. And we now have the coordinates 2 and 2 at our point of inflection. Okay, so let's just talk a little bit about, I just want to go back to what Hope was saying about where f prime x is negative and where f prime x is positive. I just want to talk a little bit about these things in relation to this particular function that we've got. What I'm going to do, I think, just to make life easier for us, is I'm going to redraw it over here where Hope, yes. So in other words, if you want to find a y coordinate on the original function, you will always sub that x back into the original. Yes, quite right. 100%. Okay, so our graph, okay, we've got purple axes now, that's fine. And our graph went through there and up here. Oh God, that's a terrible shape. My apologies, matrix, but anyway. So we've got 0 and 0. Here we've got 1 and 4. And here we've got 3 and 0. No problem, Hope. Okay, so the other thing that they love to ask us are questions about output. This is what I was talking to you about earlier. Questions about output, about gradient, and about concavity. So if I ask the question here, for which values of x, all right? And my first question to you guys is this. So this is the graph of f. Where is f of x greater than 0? What does that mean in simple language? Lovely, guys. Where is not concavity, not concavity, Hope. Okay, where are the y values positive? Yes. Where is y positive? Okay. So where is y above the x-axis? Here's our x-axis. So yes, where is the graph above the x-axis? So the graph is above the x-axis when x is a number that is bigger than. That's it. Okay, good Kanisile, good Aisha. Okay, where x is bigger than 0. That's where output or y values are positive. Now, if I ask you a question, number 2, for which values of x is f prime x smaller than 0? What does that mean in simple? Yes, to be so, quite right. What does that mean? Oopsie. That didn't come out right. Okay, to be so, not where is y negative, it's f prime x. Okay, where is gradient negative? Okay, remember f prime x is gradient. Where is gradient negative? That's what it means. Okay. So in this sort of function, okay, that's first concave down and then concave up. The graph is a decreasing function between the turning points. Okay, so for which values of x is the graph, is the gradient negative? Where are you walking downhill? Okay, so let's see if we've got an answer here. Okay, between 1 and 3, Belinda, you are right. Okay, Tisha, we're not talking about concavity just yet. Okay, we're talking about where is gradient negative. Right, quite right, Belinda. Gradient is negative over here. Look here, matrix. Okay, between our turning points. This is where the gradient is negative. We would be walking downhill. Okay, so between 1 and 3. Okay, how are we going to write between 1 and 3? Where x is greater than 1, but smaller than 3. Does that make sense, everybody? Yes, Colafela, that's it. Okay. If they asked you, question number 3, okay, if they asked us the opposite, where is gradient positive? F prime x greater than 0. Okay, where is gradient positive? How would we answer that, matrix? Cool, Hope, I'm glad it does. Where is the gradient positive? So this is where we are walking uphill. Okay, gradient is f prime x decreasing when it's negative. Okay, gradient f prime x greater than 0, that's where it's positive. Where is it? Increasing. Okay, so Aisha says between 0 and 1. Okay, why? Okay, so in other words, hang on a second. Are you telling me that the gradient over here, let's just have a look at this, right? If I wanted to measure the gradient here, would I expect a positive or a negative answer for gradient? Where I've got my yellow dot. Correct, Neo. Correct, Kanye. Yes, Buhle, I'd expect a positive answer, wouldn't I? Okay. What would be negative where the dot is yellow? Y would be negative, isn't it? Okay. So at the yellow dot, f of x is negative. At the yellow dot, f prime x is positive because we are walking uphill. Okay, yes, we are below the x-axis where y is negative, but it's still increasing. So this is an increasing function all the way from negative infinity up to your turning point. And it is a positive or an increasing function, not positive is not right, and it is an increasing function when x is a number that's greater than 3, which is what a lot of you have told me. So where is the gradient positive? It is positive when x is smaller than 0 or where x is greater than 3. Does that make sense, Matrax? Okay, so the yellow parts represent where we are walking uphill. It doesn't matter if we are above or below the x-axis because they're not asking us about output, they're asking us about gradient. Thanks, Kulani. Thanks, Kulafurla. Oh, thanks. Can you see that? It's a nice smiley face. All right, and then let's do this. We'll put in that lovely point of inflection that was worked out so nicely. Okay, and let's talk. Cool, thanks, Tisha. And now let's talk about concavity. Okay, let's talk about concavity. So now question number 4, my lovelies. Okay, f prime prime x smaller than 0. What does that mean in plain language? Concave? Yes, Cassandra. We need to talk about this. That's a very, very good question. Okay, I'm going to answer it now. Okay, can you see there? F prime prime x is smaller than 0. Concave down. Okay, concave down. Oopsie. Yes. Okay, so concavity is negative. It's smaller than 0. Okay, so concave down. Concavity is negative. Of course, one lesson couldn't be complete without my stupid board doing that. No worries, can you see it? Hang on a second, guys. As always, it's decided to just shut itself down on me. I will be back in business in 2 seconds. I wish I knew what it was that I press on this board that makes this happen.
How are we feeling, guys, so far? How are we feeling?
Hang on a second. Oh, there we go. You've got a whole lot of people writing to you, which is nice. There we go. Okay, go down here. All right, sorry about that, guys. Here we go. We are back in business again. Oh, that's lovely. Thanks for asking, Naliso. It's so nice to hear from everybody, isn't it?
Yeah.
Yeah, it really is. Okay, so now to answer this question, where is the graph concave down? Now forget about the yellow and the pink, all right? We're going to use a new color here. Let's get rid of the yellow. Oh, okay, that didn't really get rid of the yellow. Okay, let's just draw over it. Okay, concave down. Let's make this, oh, maybe that's a bit bold. All right, we'll go with pink. Okay, concave down. It's going to be concave down because A is positive. It's going to be concave down before the point of inflection. So the dark pink is where it is concave down. Okay, concave down. So in other words, if we took an x value that was smaller than 2 and we subbed it into the second derivative, we would get a negative answer. Remember, who was it Colifelo? Who told me the coordinates at the y at the point of inflection so nicely? Was it Colifelo?
It was Hope.
Hope. Was it Hope?
Yeah.
Who said
Yeah.
2 and 2? This over here. Who did this so nicely? Yes, it was Colifelo. I thought so, Tippy. So it was Colifelo. Oh, shame, Hope. Oh, never mind. Okay, so yes, so I know, so sweet. Okay, so it was Colifelo that did this for us that was so perfect. All right, look here, guys. All right, Colifelo told us that the second derivative in this case was equal to 6x minus 12. If I take a number, any number that is smaller, where's my graph now? Any number, how? Where did it go? Where is it? I feel like I'm losing my mind now. Oh, there it is, okay? So if we take any number that is smaller than 2, look here, look, I'm going to sub in 1, okay? Look here, guys, f prime prime x. Remember, Colifelo said it was equal to 6x minus 12, right? What's going to happen when I sub in 1? Equals 6 times 1 minus 12 gives me negative 6. Okay, so the concavity at x equals 1 is negative 6 because it is concave down. All right. If I now wanted to work out what the concavity was at the x-intercept, at this x-intercept over here, I could sub in 0. Okay, so now let me go and do that. Get rid of this one. And you're going to see it's going to be even more negative. Okay, so f prime prime x gives me 6 times 0 minus 12. Okay, that's going to give me a measure of concavity of minus 12. So the concavity keeps on decreasing. Okay, so becoming more and more negative. So if I want to now go and sub in f prime prime, let's say I want to work out the measure of concavity at x equals negative 2, which would be somewhere down here. We're talking now somewhere down there at negative 2. Look here. 6 times negative 2 minus 12. So that's minus 12 minus another 12. That gives me minus 24. Okay, can you see how every time I sub into the second derivative, it's going to give me a negative answer because the graph is concave down. At 2, that's where the graph stops being concave down and starts being concave up. Okay, so now if I sub f prime prime 3 into my second derivative, look here, 6 times 3 minus 12 is 6. If I subbed in 4, which is bigger than 3, or if I subbed, let's say I subbed in 6. Okay, I'd end up with 6 times 6 minus 12. That would give me 24. Okay, now the graph, after the point of inflection, the graph is now concave up. So here where I'm doing the darker blue, it is now concave up. Okay. Can you see how we got negative numbers when it was concave down and positive numbers when it was concave up? All right. So the graph is going to be concave down when x is smaller than 2. So where x is smaller than 2, the graph will be concave up. In other words, f prime prime x greater than 0 when x is greater than 2. Okay, does that make sense? Okay, so just like gradient has a value that we can calculate, concavity has a value that we can calculate. Okay, these are things that are measurable. Okay, so we can know, as far as gradient is concerned, we can know how steep. Okay, as far as concavity is concerned, we can measure how concave. Okay, concave up or concave down. All right, is that making sense to everyone? All right, yeah, Shane, you've been asked this 1,000 times tonight. Okay, good stuff. Are there any other questions before we end off?
We have a quiz today.
We do have a quiz today. Yeah.
Today is quiz day, so I'm going to put the link on the chat.
Awesome, Nelisva. Thank you so much. Perfect. Any last questions before we go, guys?
Watobe has a question.
Sure, Watobe, go for it.
Ma'am, so for the first derivative is it for concave? Like, can you please repeat what first derivative is for, and for the second derivative, if ever we get lost in the test?
Absolutely. Okay. So here it is again for you, Watobe. It's here in orange. Okay. So f of x is output or y value.
Okay.
F prime x, the first derivative is gradient. This is the first derivative. Okay, your f prime prime x is your concavity. That is your second derivative.
Thank you, ma'am.
Okay, no problem. No problem. Oh, sorry, Cassandra, what was your question? Oh, I'm sorry, Cassandra. What were you asking me? And Tisha, I'm going to answer your question right now. Tisha, I'm just looking at your question here. Tisha, use the quadratic formula. Okay, if it's not easy to factorize, don't stress. Just make sure that you sub into the quadratic formula and show that you've subbed in. Yeah.
Ma'am, I asked whether it was, if it made a difference if we subbed, instead of or, we said and.
That's it. That's it. That was such an important question. Yes, Cassandra. Yes, 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 yes. You cannot use the word and when you are talking about x values. So in other words, if I have an x coordinate, let's say I've got an x-intercept, okay? My x-intercept is at x is 0 or x is 1. Okay, because it cannot be both at the same time. Okay, Cassandra, x cannot be 0 and 1 simultaneously. Either it's 0 or it's 1. Okay, when we use and in maths is I can say to you at the turning point or at one turning point, x is 1 and y is 4. Then I can use the word and because both are happening at the same time. Okay, so Cassandra, if they say to you, and a question with an inequality, so like here, where is gradient positive? You cannot say x is smaller than 0 and x is greater than 0. Okay, because it cannot be both at the same time. So it's either where x is smaller than 0 or where x is greater than 0. Does that clear that up? It's a very, very, very important question. If you use the word and incorrectly, they will penalize you at end of year marking. Okay, I'm so glad you asked that, Kashandra. That was a fantastic question. All right, Tisha, we certainly can do. I never ever teach the long division method just because I think it's so nasty, but if you want me to do an example with you, then I am more than happy to do so. Okay. All right. Kanisila, you've got a question? Go for it.
Ma'am. When we were finding the when we're using the first derivative to find a stationary point, if I'm not mistaken, ma'am, if we had to substitute the x value back into that equation, the first derivative,
yes,
is that dangerous?
No, it's not. They can ask you to do that as well. And I mean, that certainly becomes important when we start talking about tangents and stuff like that. But just like you saw me subbing different x values into the second derivative to get a value for concavity. So we can do the same thing for the first derivative. So remember, in this case here, our first derivative, if I recall correctly, was 3x squared. Was it plus or minus? I think it was minus 12x plus 9 or something like that. Is that right? I think so. Okay, all right. Now, let's take a point on the graph where we know that it's going to be an increasing function. So let's say where x is equal to -1, okay? Because we know that somewhere over here, that's where x is equal to -1, and we know that we'd be walking uphill at this point. Look what happens. You're going to get a positive answer. Look here. So f prime 1 means what is the gradient when x is equal to, oh, sorry, it was -1. What is the gradient when x is equal to -1? That's what f prime 1 is. So 3 minus 1 squared minus 12 times -1 plus 9. So this is going to give us 3 plus 12 plus 9. Can you see how we're getting a positive answer here? Okay, we would end up with 24. Does that make sense to you?
Yes, ma'am. Yes, ma'am.
Okay, now if I want to work out what the gradient is when x is equal to 0, I'm expecting a smaller answer than 24, but still a positive one. So now if I work out f prime 0, so 3 times 0 squared minus 12 times 0 plus 9, look there. Can you see it's positive, but it's getting smaller because I'm approaching my turning point? Okay, if I now sub in f prime 1, I'm going to get 0. Look what happens when I sub in f prime 2, where the graph is decreasing. We're going to get a negative answer. So this is going to give us 12 minus 24 plus 9. Okay, we're going to get an answer of -3. Okay, so can you see that's what I was trying to say to you earlier about how concavity can be positive or negative or 0. Gradient can be positive or negative or 0. So the gradient at a particular point, so the gradient at 2 is -3 when you sub 2 into the first derivative. Okay, the gradient at 0, sorry, yes, at 0 is 9 when you sub 0 into the first derivative. And that's what calculus is all about. It's about how these things are changing. Okay.
So, ma'am, would this also be applicable when we trying to find the stationary point, the y value? Or
So if you were trying to find the y coordinate at the turning point, you would take the first derivative, solve for x, And then you would have to sub those two x's back into your original to find the corresponding y coordinates.
Okay, so ma'am, we can never ever substitute those x values back into the function.
If you sub those, you can sub those x values. If you sub them back into the original function, it gives you the corresponding output at the turning point. If you sub those x values back into the first derivative, it gives you the gradient at that point.
Oh, okay.
Does that make sense to you?
Yes, it does, ma'am.
If you drop it, if you sub it into the second derivative, it gives you the concavity at that point. Okay, so if you want the corresponding y value, you've got to go back and sub into the original equation. So in other words, what we were doing, where is it now? Did I rub it off? This is what we were doing. Okay, so here in orange. Okay, so we wanted to work out the corresponding y coordinate when the x coordinate was 1. So we subbed 1 back into the original. What happens when I sub 1 into the first derivative? I've just shown you. All right, so if I sub 1 into the first derivative, and I didn't sub in 1, I subbed in 2. Now I'm getting a measure of gradient. This is gradient, it's not output.
Okay. Thank you, ma'am.
Okay, it's a pleasure. I hope that makes sense.
Yes, ma'am, it does.
Okay, all right. Bye, Kanisile. Bye, everybody.